we've just seen that if we take just the I and j components out of the function r of t, we get a function r1 of t, calling it r1 of t, cosine of ti plus 2 sine tj, whose graph is an ellipse and which we can tell is traversed in the counterclockwise direction as t increases. Now let's think about what we're going to do with this 1/2 k, 1/2 t times k. Excuse me. We can we've already let r1 of t equal cosine of ti plus 2, remember the 2 this time, sine of tj. That gives us a lot of our function r of t. The rest of it's just the 1/2 tk, so why don't we just let r2 of t equal 1/2 t times k. Then our original function r of t is the sum of the function r1 of t, the function that describes ellipse in the xy plane, and r2 of t, a function which a vector function which points along the positive z direction, points up out of the xy plane. And as t increases, the value of this function, the magnitude of this function increases, so we get an increasing vector along the z-axis. We can sketch the implications of this breakdown. We can sketch the ellipse in the xy plane. Excuse me, I don't know what's blooming out there, but something's getting me. And if we start, I've elongated this ellipse in the wrong direction, but we're going to use it to represent our function anyway. Okay, we move along this ellipse in the counterclockwise direction, and this is the ellipse described by r1 of t. So we think of a series of vectors moving around this ellipse. Well, we might as well complete the picture and draw a couple more. Okay. Now, what's r2 of t? Okay, this is our r1 of t. r2 of t, if we sketch it here, at any time this is a vector parallel to the k vector. If t is positive, then here's what r2 of t looks like. And as t gets bigger and bigger, the magnitude of this vector gets larger and larger. So we can imagine if we start for small t, we get a small vector, then a larger t, we get a larger vector, and the greater t gets, the longer this vector gets. This vector is always rooted at the origin, so each of these tips represents a longer and longer vector. What happens if we add these various r of t vectors, r2 of t vectors, to these r1 of t vectors to get an r of t vector? Well, if we come out here, our r2 of t is a fairly short vector. Come to this point, let's say here, r2 of t is somewhat bigger. Come around to here, r2 of t is going to be even bigger. And as our t values continue to increase and we move around the ellipse, we're going to add longer and longer vectors. By the time we get around to the positive x-axis, this vector will be pi units long. because we'll move 2 pi. Well, to get around the circle, t has to change by, or the ellipse, t has to change by 2 pi, which means that 1/2 t is going to change by pi. So that our curve, our path, is going to look something like this. A helix rising up above the xy plane, and the cross section of this helix is always the ellipse that lies above this ellipse in the xy plane. So that by considering our vector function just in the xy plane and then superimposing the motion implied by the tk component of our original vector, we obtain this picture. And we can fill this in, shade it a little bit, get an idea of what that path looks like.